Okay, folks, this is section 3.3. It starts talking about dividing polynomials. Some of the stuff should be reviewed for you. Try to get this done in a brief amount of time so you can start working on your assignment. We're going to do long division of polynomials. We'll then see how we can use synthetic division to kind of shorten that process. And then towards the end, introduce the remainder and factor theorems. Let's see here. So long division polynomials. What is important, guys, is to first realize that even though we're doing long division of polynomials, it's the same as long division that you've ever talked about in elementary school. Okay, with dividing just real numbers. Here we see this kind of notation: 38 divided by 7. Okay, and you can rewrite it. Most of you are probably maybe more comfortable with seeing this as written, especially when we start with polynomials, as 38 divided by 7 that way. Okay, but the 7 is referred to as the divisor. The 38 is what we call the dividend. And then once we start getting a solution for what this is, okay, 5 is referred to as the quotient. And then we have you guys are going to have back to, like, you would do the 35 here. Let's just subtract, give you 3. Now, you know that this is a remainder because it's less than the divisor. Okay, so you would maybe in 3rd grade put R 3 for remainder 3. Okay, but we've also realized that, well, that means a remainder of 3 out of 7. Okay, so we have 5 plus then 3 7. So we're gonna write it that way. Why do we like writing it this way? Because when we see in a moment, we're going to have a idea that says that if I take my quotient of 5, multiply it by my divisor of 7, and then add to it my remainder, I should get back to 38. Okay, so this was the divisor times the quotient plus the remainder should then equal my total, or maybe right this way, my dividend. But that's something that we've known from, forever, I guess, in regards to mathematics. And doing that in, 3rd, 4th grade. But now we're going to kind of move that over to dividing with polynomials. Okay, so it says this is called the division algorithm. A lot of times referred to as maybe Euclidean division algorithm. And if you remember who Euclid was, same guy. Okay. Obviously, Euclid was the geometry guy, right? Okay, so it says if p of x and d of x are polynomials, okay, with d of x cannot be 0. So basically what's going to happen here is polynomial, this will be your dividend, or sorry, your dividend. This is going to be your divisor, and our divisor we just can't divide by 0. So we know that. It says then there exists a unique polynomial q of x, a quotient, and r of x, a remainder, where r of x is either 0 or of degree less than the degree of d of x, meaning that my remainder is less than what my divisor was. And it says such that p of x divided by d of x, so your original polynomial divided by your divisor, is equal to a quotient plus your remainder divided by your divisor. Okay? Or what we really like to do is this: rewrite that as the dividend is equal to your divisor times your quotient plus your remainder. So this here was like writing it as 5 plus 3 over 7. And this over here was like saying 38 is equal to, I think my divisor was 7, my quotient was 5, plus my remainder of 3. Preferably with polynomials, this method here, this arrangement of objects is going to be probably preferred. It says the polynomials p of x and d of x are called the dividend and divisor respectively. Q of x quotient, r of x the remainder. Okay, so just kind of get into doing this process, do some examples here. It says divide 6x squared minus 26x plus 12 by x minus 4. So express each, or the result in each of the two forms of the division algorithm. All right, so the first thing we got to do with this, guys, is understand that we need to have our dividend to be in descending order, and if there are any variable terms that are kind of missing, we want a placeholder. If you remember doing that in Algebra 2. So if I had like, if this was just 6x squared plus 12, if that wasn't there, I would have to put a 0x in here just to make sure that I align things correctly. You can do it without those things, but you're going to have to do a lot of thought in regards to making sure that you line things up. It's just so much easier if you put those placeholders in. When we get to kind of shortening this process through synthetic division, and it's an absolute necessity that we put the placeholders in. All right, so kind of the thing that we do here is not necessarily thinking about division, but in regards to understanding what needs to show up here as my quotient. But we kind of think about what does my quotient look like if I'm going to multiply it by my divisor, okay, to get my dividend. So we're kind of almost working backwards. It's almost like the idea, like if I had 38 here in my 7, I'm asking myself, okay, what can I put here? Instead of saying how many times does 7 go into 38, we're kind of thinking about what number can I multiply by 7 to get something either equal to or less than 38, okay? So here, the idea is if I put a 6 right here, okay, I'll have 6, and I'll multiply that by this, and I'll get 6x minus 24. Well, that's going to line things up here. So I don't want 6, just a 6. I want a 6x right here. Because now, what I'm looking for, when I multiply this, essentially, I guess the quick kind of cheat to this thing is, what can I multiply that term by? Don't really worry about the minus 4, but what can I multiply that term by so that I get that term? And then everything else should kind of fall in line. So when I have 6x, 6x times x gives me 6x squared. Now 6x times negative 4 gives me negative 24x. Okay. Now if we look at this, so we're going to line our things up, line our terms up. What we'd like to do is, because you guys remember this, so if this would have been 5, you put 35 here, 5. And then you would subtract, you would get 3. Well, subtracting this stuff sometimes is difficult, okay? So I'm just going to go through, this is the way I always do it, multiply everything by a negative. So I go through and change all the signs in this blue phrase, and then we're going to add straight down. So 6x squared plus negative 6x squared, those go to 0, so don't write that. Now I'm going to have negative 26x plus 24x, so it gives me negative 2x. And then I bring down all my other terms that really didn't have anything written underneath them. Okay, so now I go on and just kind of repeat the process. Now it's what do I multiply by this term here to get this negative 2x value? So it's got to be minus 2. So take negative 2 times x gives me negative 2x. And now negative 2 times negative 4 gives me positive 8. I'll negate everything and then add straight down. So it gives me 0. And now the 12 minus 8 gives me 4. Okay. So now this thing here, I have a remainder of 4. Okay. So when they ask the two different methods of writing our solution, the one was when I take p of x divided by d of x, and that should give me my quotient of x plus my remainder of x. So in this case, if I have 6x squared minus 26x plus 12 divided by x minus 4, I can rewrite that as a quotient plus a remainder as 6x minus 2 plus 4 over x minus 4. Okay. Now, that is not equivalent to this. Okay, it's not equivalent to my numerator. It's equivalent to my numerator divided by my denominator over here. So that's one method of rewriting our answer. But another method that we kind of prefer is just a little bit of algebra. Think about what happens here. Just real quick, I want to jump back to, so this method, this format here is this format right here, with the quotient plus the remainder over your divisor. If we just go to this thing right here and multiply everything by d of x, left-hand side and right-hand side, just assert d of x there. Obviously, they cancel there, but it gives me my quotient. I guess I did have that there. I forgot to put that there. I'll have my p of x is equal to now my quotient, q of x, times my divisor. Now my d of x times the d of x here, on top, on the bottom, will just give me plus my remainder. Okay, so once I have this, if I multiply everything by x minus 4 now, so x minus 4 will cancel here. It'll give me, obviously on the left-hand side, 6x squared minus 26x plus 12 is equal to, now it'll be this thing here times x minus 4, so 6x minus 2 times x minus 4, plus now, well, if I multiply this by x minus 4, I multiply this by x minus 4, so it just leaves me my remainder of plus 4. Okay, so here's the thing. I like this form. Okay, so it says p of x is equal to your quotient times your divisor plus your remainder. Okay, if I were to FOIL this out and add 4 to it, it's going to get me back to that. Okay, why is this beneficial? Because it's really nice when this remainder turns into a 0 eventually. Because when that turns into a 0, if you think about what we've done, we've factored in a polynomial. Okay, so the hope is that we eventually get that to be a 0. So but that's the general practice of dividing a polynomial by another polynomial. So we go through and you see this kind of works through and gives you the solution. All right, let's see if we can get the same process but use synthetic division. Okay, so synthetic division, guys, is the same process. Now, synthetic division we can only use right now with the divisor that is linear. Okay, so this stuff we could divide by anything out here that we wanted to, as long as obviously that's a less degree than what we have here, equal to or less than what our leading degree of the dividend. But with synthetic division, we want to just divide by linear factors. Okay, so synthetic division is a quick method for dividing polynomials. You'll be using the divisors in the form of x minus c. It says in synthetic division, we write only essential parts of the long division. It says compare the following long division and synthetic divisions in which we divide these two things. So we'll go ahead and we'll do this the long division way. So let's see here. So the long division way. Now I like this one because it does force us to have a placeholder here. So x minus 3, put my divisor outside. 2x cubed minus 7x squared. I will put my 0x in there, and then plus my constant of 5. So now I need to think about, obviously it's got to be a 2x squared here to multiply by that x to get 2x cubed. So it'd be 2x cubed minus 6x squared. So negate and then add straight down. So those are going to go away. That's going to be negative x squared. Now drop down my 0x and then my plus 5. Okay, so anything that didn't have something to subtract gets brought down. All right, so now I just play that game again. I'm looking for now something to give me negative x squared. So it's going to be obviously negative x. So negative x times x gives me negative x squared. And now right here, you're going to see the reason or the purpose for having this placeholder, because now negative x times negative 3 gives me a positive 3x. And I just want to make sure that I never line that. If I didn't have my placeholder, this would have lined up underneath the 5, and we'd have to think about what we have. But now we will negate and add straight down. So it gives me negative 3x. Bring my 5 down. All right, so now I need a negative 3 here. Multiply negative 3x to be positive 9. Negate, add straight down. So now I get negative 4 as my remainder. Okay, so I would write this as, if I'm going, the p of x is equal to the quotient of x times the divisor of x plus my remainder of x. I would write this as 2x squared minus x minus 3 times now x minus 3 minus then 4. If I were to FOIL that thing out, it's going to give me back to this original p of x. Okay, so let's see how this kind of works with what we call synthetic division. If you remember, synthetic division is just a shortcut for this process. You put in your coefficients only. So I have 2, I have a negative 7, I have a 0, and I have a 5. I need to have that 0 in here because we are losing all kind of understanding of variables here, where it'd be really hard to see what's going on if I don't have that placeholder. Now what goes in here is actually the opposite. It's actually the 0. If x minus 3 is going to be a factor, then the 0 is what would go here. Now, not necessarily is this going to be a 0 because of just the process that we're going through right now. We're just going to see everything that we can divide. So we might get a remainder that's not 0. In this case, obviously we get negative 4 as a remainder. But basically what goes in the box is the answer to, or the solution to that equation right there. Okay, so we're going to put 3 in the box. So now what happens is that we bring down our always bring down that first coefficient. So it gives me a 2. Now we'll take the 3 times the 2, and that product goes right here underneath this one. Okay, so it gives me a negative 1. I'm going to add straight down, it gives me negative 1. Now I'm going to do the same thing. Take my 3 times my negative 1, and that's going to go right there. So it gives me negative 3. Add straight down, gives me negative 3 again. Now I'll take my 3 times that negative 3, and that product goes right here, which is negative 9. Add straight down, gives me negative 4. Okay, this last object here, the last what we call coefficient, is actually your remainder. Okay, and these are the coefficients of what we call our kind of our depreciated polynomial. Okay, this is our quotient right here. This is q of x. Now think about this. This was a linear term. Okay, that 3 came from x minus 3. This was x cubed, 2x cubed. So a 2x cubed divided by a linear term is going to depreciate it to an x squared. Okay, so it tells me my quotient is 2x squared. And these will all then be in descending order. 2x squared minus 1x minus 3. And then my remainder is negative 4. So I'll write this as, there's my remainder, here's my quotient, and again, that was my divisor, x minus 3. Okay, so if you look at how we compare these, it's the exact same thing as that. But the hope is that we realize that this is a little bit more efficient, a little bit quicker. Now, if I want to divide by like x squared minus 3, I can't do that with synthetic division. Okay, at least right now. Well, we can maybe break that up into like 2 iterations of synthetic division, but this would probably be a little bit easier. All right, so got that. This is just going through the example, showing you the step-by-step stuff. So, all right, so it gets us to what we call the remainder theorem. Okay, and eventually the factor theorem. The remainder theorem says the next theorem shows that synthetic division can be used to evaluate polynomials easily. It says if the polynomial p of x is divided by x minus c, then the remainder is the value p of c. Okay, if the polynomial p of x is divided by x minus c, then the remainder is the value of p of c. Okay, so with the remainder, I just want to kind of quickly prove this because it is a pretty simple proof. It says if the polynomial p of x is divided by x minus c, the remainder is the value p of c. What we mean by here, okay, so any polynomial that we take, okay, so let's just say p of x. We know, based off of what we just did with the long division, that that's going to give me a quotient times then my divisor, okay, plus then my remainder. Okay, well, right now here, we're saying it's divided by x minus c. Okay, so we're saying then p of x is going to be my quotient of x. Now my divisor is x minus c, so I'm going to replace this thing here with x minus c plus then my remainder. Okay. Now my remainder is not going to be variable, so it's not r of x. Okay, because it's just going to be a constant. Because we're dividing by something that's linear here, so we'll have a constant remainder. Okay, so what's this mean? It says then the remainder, if it's divisible by it's divided by x minus c, the remainder is the value p of c. Well, if I evaluate this thing at c, let's see what happens. P of c is equal to q of c. Now, c minus c here, okay, because that's what the x value is now, right? It becomes c plus r. So now, p of c is equal to, think about this is qc, this is 0. So you have some quotient times 0, which is just 0. So we see here that this is the proof that shows that p of c is equal to the remainder. And it's the remainder there. Okay, so I'm going to show you what this means kind of in a specific case. All right, what this is doing in a specific case. It says let p of x equal 3x to the fifth plus 5x fourth minus 4x cubed plus 7x plus 3. It says find the quotient and the remainder when p of x is divided by x plus 2. So I'm just going to do the synthetic division here. So I'm going to put negative 2 here. Remember, because we always put in that box the solution to that little equation. I'll put my 3, 5, negative 4, 0, 7, and 3. Bring my 3 down. Multiply gives me negative 6. Negative 1 gives me 2. Negative 2. 4. Negative 8 here, so negative 1, and then 2, so it gives me a remainder then of 5. Okay, so we get a remainder of 5. So when we evaluate this thing at negative 2, the remainder theorem should tell us that we get a remainder of 5 back. So that's what they're trying to ask us down here, find p of negative 2. So that would be this idea. It'd be taking 3, negative 2 to the fifth, plus 5, negative 2 to the fourth, minus 4 times negative 2 cubed, plus 7 times negative 2 plus 3. Okay, just to kind of expedite things here real quick, let's see if I can find just a quick calculator to do that for us. All right, so we have 3 times negative 2 to the fifth, plus 5 times negative 2 to the fourth, minus 4 times 2 cubed, plus 7 negative 2 plus 3. What do you see we get? We get 5 back. Exactly the same thing that the remainder theorem tells us. If you evaluate at negative 2, okay, you get 5 back, which is the remainder of the division of 3x to the 5th, that long polynomial, by x plus 2. That's all the remainder theorem says. But there's a lot of consequences of the remainder theorem that are pretty nice for us. All right, so keep going through. It's just showing the work for those. All right. Here it says C is a 0 of P if and only if x minus C is a factor of P of x. There's kind of two things going on here. It says C is a 0 of P if and only if x minus C is a factor of P of x. If you remember from geometry, that means if C is a 0, then x minus C is a factor of P of x. That's the first thing that says. The second thing that says is the kind of the converse of this. If x minus C is a factor, then C is a 0 of P of x. Okay, so this kind of makes a little bit more sense in regards to how we go through the proof of this, because it's called a biconditional. So if we're going to prove it, we got to prove because the if and only if we have to prove both of these statements. It says if C is a 0, it's better written for us. Now it is the exact same thing. If you go back to what we talked about in 3.2, it says C is 0, then P of C equals 0, saying the same thing. Okay. Down here it says if x minus C is a factor, then P of C is a 0. All right, so proving this first one, we know that, so let's put 1 here. We know that P of x can be rewritten as our factor x minus C times our quotient. So this is our divisor, sorry, which is hopefully going to be a factor. Our divisor times our quotient plus then our remainder, okay? Well, our remainder, if you go back to the remainder theorem said that your remainder is equal to your polynomial evaluated at C. Okay, so instead of putting like R here, we just put P of C. Now, why is that useful? Because directly then, if P of C is a 0, that's what this says here, we'll make that substitution. Because the if part, remember, that's given. That's happening in front of us right now. We know that to be true. So we can use that in our proof. So P of x equals x minus C times Q of x plus then 0. So ultimately just leaves me P of x is equal to this thing, okay? And what do we got going on here? You got two things. You got x minus C, whatever that is, times Q times x, whatever that is, some other polynomial. Those things multiply together to give me this. Well, isn't that the definition of what a factor is? One of multiple things to multiply together to give me some product. Okay, so this shows that we've proven this part of that theorem. Okay, now the second part of the theorem is if x minus C is a factor, okay, then P of C equals 0. So let's go ahead and do that. It says P of x. Now, if x minus C is a factor, that means that we have no remainder. Think about this. Think back to 30 divided by 6. Well, it gives me 5. That means 5 is a factor of 30, and so is 6. Look at the remainder. Its remainder is 0. Okay? So P of x is equal to x minus C times my quotient of x. Okay? Now, it says if x minus C is a factor, then P of C equals 0. Well, we're evaluating if x minus C is a factor. Let's see what evaluating at C looks like. So if I evaluate this thing as C, P of C is now equal to c minus c times q of x. Okay, well, what's c minus c? 0. So we get 0 times q of x. So p of c then is equal to 0. Okay, so if x minus c is a factor, which is what that's saying right there, that's what we start with. That's our given. Okay, then p of c equals 0. Well, does that happen? If I evaluate as c, do I get 0? Yes, I do. Okay, so a lot of times when we're done with the proof, we write like Q, E, D, which is, this is a Latin phrase, but and I can't pronounce what it says, but basically says that what we were asked to prove, we've done. We've demonstrated what we set out to demonstrate. Sometimes that takes place with putting a little square there. I forget what it's called or who's named after it, but they refer to that as a tombstone. It's kind of weird, but I forget the guy's name. It starts with an H, who's named after. But that just kind of tells us our proof has been completed. All right, so let's use these things. How do we use these things? Let me check how we're doing on time real quick. All right. All right, it says, let p of x equal x cubed minus 7x plus 6. Show that p of 1 equals 0, and use this fact to factor p of x completely. All right, so this is getting down to kind of the, we've talked about how we don't have the tools yet to really factor anything other than a select few polynomials that are maybe of quadratic form or maybe some really nice convenient cubics or whatever, but in general we don't have the ability to factor real well larger polynomials. So this is going to start to set that up for us. Okay, basically says show that p of 1 is equal to 0 and use this fact to factor p of x. Well, obviously you could do this. You go p of 1 is equal to 1 cubed minus 7 times 1 plus 6. What's 1 minus 7 plus 6 does equal 0. Okay, so the remainder theorem is telling me that that is 0. Okay, now the factor theorem is saying, well, if the remainder is 0, if p of c equals 0, then x minus c is a factor. All right, so basically they're just trying to get us to go and write that x minus 1 is a factor of this thing. Okay, now if x minus 1 is a factor of that, what is the quotient when I divide that thing out? Okay, so I'm looking now for what goes in this little box here, or not box, but this extra set of parentheses. So how am I going to do this? I'm going to use the split division approach. The coefficients 1, 0, negative 7, and 6. Bring the 1 down. And now I get a 0 right here. And that's nice because now it tells me if this was x cubed, it's depreciated. This was a linear term. So it depreciates down to x squared. So now right here I'll have x squared plus x minus 6. Okay. That is a factored form of x cubed minus 7x plus 6. Now we can go further. Because what is this? It's quadratic, and we have the ability to factor quadratics. So now this thing's going to be x minus 2, x plus 3. And now we've effectively factored our first cubic polynomial in which we didn't have any other technique to do this. Okay. Now they are helping us. They're providing us with that C a try. All right. So without that, we really still are lost. But they're going to give us that information here in the first couple of sections, or first couple problems that we do. Okay. Later on, if you guys remember from the P over Q stuff, basically look at the factors of this divided by the factors of this coefficient. Give me good starting points for these numbers, and we'll talk about what we call Descartes' rule of sign and that kind of stuff. That helps us kind of maybe break that list down later on. But we'll get into that maybe tomorrow or the next day. So I believe this just goes through and shows you. So hopefully that helps with understanding what these theorems are and how we're going to use them. I do want to go to WebAssign and do one of these problems with you. This one here. We kind of started with this on Friday. But I want to show you how to kind of address this so that we do end up with the correct function here. It says find the polynomial of the specified degree whose graph is shown. Okay. Obviously, we know that we're going to have a 0 at -2. Okay. We have a 0 at +1. We have a y-intercept at -4. Okay. So 0, -4. So now this 0 of -2, because we're tangent there, it's a multiplicity of 2. Because we're going through this one here, it's a multiplicity of 1. Now they say find the polynomial of the specified degree whose graph is shown. They want degree 3. All right. So we know that this is that 0. If that's the 0, then x minus that is the factor. So minus a -2 would be +2. Now it's a double root, so it shows up twice. And then over here we have x plus 1. Okay. Sorry, x minus 1. X minus 1 is to the right. Okay. X minus that is always the factor. Now what I would want to do, guys, is just make sure. So this is p of x. Normally, so there's an infinite number of functions that look like this. They go through that 0 and that 0, but there's only one that goes through that y-intercept. So I'm going to make sure that I have the right a coefficient out here. If we look at this, it's saying that it should be a 1. I just want to validate that. So the p of x, so remember this is an x value, and -4 is a p of x value. So I'm going to plug -4 in here. There's a, so that gives me 0 plus 2 squared, 0 minus 1. Excuse me, -4. This is going to be what? -4a. So then I divide, obviously, then a does end up being 1, so I can put that there. Now I've got my function, okay? We'll do quite a bit of that throughout the year with different functions. Polynomial right now, maybe we'll see some rational functions towards the end of this chapter. We'll do with logarithms and exponentials and that kind of stuff. Kind of looking at a graph and working our way backwards to come up with the equation that that graph is developed from.